here's a problem that at first glance can seem fairly intimidating. It says verify that near 0, sine of x is approximately the same as x. Well, how would I go about doing that? Well, I might observe that this is a function. Okay, that's a function that curves. I know that's a sine wave. Okay, this is also a formula for a function, but this is a linear function. So we're saying a function that curves is approximately a linear function. Ooh, near a point. That's going to be my point of tangency. So this is just a fancy way of saying find the tangent line to sine x at 0. Oh, and by the way, the line is going to be just L of x or y equals x. That's what you're going to get. Just confirm that. So it's essentially saying find the tangent line, it's this. Prove it. Okay? So if I'm finding a tangent line, I need two things. I need a point and I need a slope. The x value was given as 0, although it was sort of indirect. We had to translate the directions. And then the y value will just be sine of 0, which is 0. So that's f of 0, which is sine of 0. Okay, finding the slope is always a two-step process. Find a formula for the derivative, and then evaluate it at 0. So the derivative of sine I know is cosine. F prime of 0 then is cosine of 0, which I know is 1. Okay, so we want the line through the origin of slope 1. I do know that that's just y equals x. Here I can go straight to the equation because I've essentially got my y-intercept and my slope. Of course, if I did my usual rise equals slope times run, I'll get the same thing. My rise is just y minus 0. The slope was 1. The run is x minus 0. So when you're using the origin as your point of tangency, which of course you can only do if the origin is on the graph of the curve, the rise is just y and the run is just x. So we get y equals x, and of course I might choose to call that L of x equals x to say, oh, yes, this is the y value on the tangent line. This is the y value on the curve.